So this example problem has a really hypothetical case that's still worth studying because it gives great practice into applying Newton's laws when it comes to uniform circular motion. So what I'm picturing here is something like an air hockey table. So here's the puck, and we say it has a mass of m, and then there'd be all these little holes in the air hockey table blowing air upward. And so the point is it's a frictionless surface. So if you had the system set up like this, without a doubt, the puck would accelerate this way, and the weight would accelerate in this direction. I didn't state it clearly, but I think you can see what's happening here. You've got a string connecting the puck, and then it goes through a hole that's drilled in the table, and then another weight hangs from that same string down below. So this is why I say it's entirely hypothetical. I've never really seen this set up before, but it still challenges our concepts of uniform circular motion and Newton's laws. So yeah, that trick here is not just to set it up like this and let it go. We know what will happen in this case. It would really be something like a modified Atwood's machine, and I believe the acceleration of the system would then just be g times the quantity capital M over lowercase m plus capital M. I'll leave it up to you to verify that. So let me delete this. No, here's the case. I want to figure out how fast would you have to spin this puck if you hit it. Give it a whack here. Oh, what did I do wrong? Yeah. Hit the puck so that the top view would look something like this. There's the hole in the table. There's the puck. And if you hit it just right, it'll spin around in a circular path with uniform circular motion. Okay, so how can we determine what that speed would be? Well, let's make some free body diagrams here. One for the puck and one for the hanging mass. All right, so normal force and mg and tension. And there's no friction, right? Well, the normal force and the weight of the puck are going to cancel each other out. So you're left with some net force acting on the puck by the tension in the string. And likewise, capital Mg and T. And in this case, I've drawn them the same length, because the point is to try to hit this so that it spins around in a circle without making this mass rise or fall. So here we just have a case where T is equal to capital Mg. Now let's come back to this idea that there's a net force provided by tension. In this case, that net force does not accelerate by increasing the speed of the puck. It's not going to have motion along a straight line path this way. It will have an acceleration this way, but that acceleration will not be a change in speed. That acceleration is a change in direction. In other words, it's a centripetal acceleration. So m times centripetal acceleration is equal to the tension. That means mv squared over r is equal to the tension. But if we look here, the tension has to equal the weight of the suspended mass. So we simply have mv squared over r is equal to capital Mg. So the speed that the puck would have to spin with would be equal to capital Mgr divided by lowercase m square root of all this, right? Okay, so let's say the string segment that's horizontal on the table is 30 centimeters, and let's say the hanging mass is 200 grams, and the puck is 150 grams. How fast would it have to spin? The speed would be the square root of 0.2 kilogram times 9.8 meters per second squared times 0.3 meter, all divided by 0.15 kilogram. Grab a calculator and see what we get. And the speed comes out to about 1.98 meters per second, or we can round up and say very nearly 2 meters per second. Okay, if you were to hit it any faster than that, it would require a greater amount of tension. And so if the tension in this free body diagram became longer, that means the tension in this free body diagram is also longer. They're the same amount of tension, right? It's all one piece of string. But if that happens, then this weight would start to lift upward. And likewise, if you spun the puck too slowly, the weight would fall, and ultimately the puck would have both a change in speed and a change in direction. So if you watch my next video segment, I have a demonstration where I've done this same sort of thing. Instead of using a hockey puck on an air table, I have a glass tube, a string is fed through there, and a washer is attached to the end of the string, and then down below, I believe I have a stuffed teddy bear. And as long as this washer is spun with just the right speed, then the teddy bear remains perfectly suspended due to the balance between the tension and the weight. So tune into that next demonstration, and as always, thanks for watching.